Alright, welcome to another AQA A-level chemistry video. Today I'm going to be making a video on pH curves and titrations. I'll be splitting this into a 3-part series of videos on pH curves and titrations. This video in particular is just going to be about talking about titration, the techniques associated with titration, the things that you look at before titration, as well as considering information that we can gain from a titration and things you have to maintain during a titration, such as accuracy, the type of indicators that we'd use. On top of, obviously, we're doing it with titration that we can use the information to trying to use information to allow us to generate quantitative data, right? You could use qualitative, but generated is quantitative data. So producing a graph, and we're looking at a graph on one particular type of reaction, which is a strong acid/base titration. But ideally, remember, from a titration, we're trying to understand, trying to gain type of quantitative data, and the biggest one of that is concentration. Now, we have an unknown concentration and a known concentration. We use the information of known concentrations and unknown concentrations to help, known concentrations, known volumes, and known moles to help us work out our unknown concentration, right? So this requires calculation before our reaction, but also it would require us to actually do the reaction to complete the information that we need to help do our final calculation at the end. Because that's the whole point of titrations, to help us with our calculations. And at the end of this video, I'll be talking about how to actually go over some of these calculations, because I know, I mean, you guys probably already know how to do concentration is equal to moles over volume, that type of reaction. But just kind of, so that type of equation and calculation. But I'll be going through it just briefly at the end, and just converting it. You know, if you want to work out the moles from the concentration and volume, how to do that. But you guys should probably already know how to do that. Anyway, let's go straight into the video. So, key titration techniques. So here's a quick recap on the key titration information. So above are labeled images of a burette and a pipette. Now the technique in a titration, you want to calculate the concentration of an acid or base by reacting with a known amount of base or acid. Now to do this, you add a measured amount of one to the other, and you use a balanced equation to calculate the concentration. So we do our calculation first. So if we have a known, we're trying to work out the concentration, but we have the, we have the, we're trying to say, I don't know, rephrase that. We're trying to work out the concentration of our unknown sample. Now we use a concentration of a known sample and moles of a known sample. We need to calculate the volume of our known sample to actually add into our burette. And then we can use, if we already know the volume of our unknown concentrated sample, this can be used for our calculations at the end. But we need to have some information that we need to calculate before we actually do our reaction. So the volume of the known sample that we'd need for that type of reaction, and then towards the end we can then work out the titer volume, right? So all these things are important for us before we actually do our reaction. And obviously during the reaction, we'd use a burette to load our either acid or base that we're going to be titrating with. We use a pipette which has a graduation mark on it, telling us the graduation mark is usually 250 centimeters cubed, and we use that to load a solution in either an conical flask or any other type of beaker. But a pipette is used to just, you should already know by now, but a pipette is just used to load a solution into it so we can help transport that solution to another beaker or another conical flask. Now burette, you can use it to load it into a burette, but the reason why I don't say it generally because the burettes are quite tall, and unless you're doing it on the ground, I wouldn't suggest that method. I suggest loading your sample. If you're loading anything into a burette, I'd suggest getting a beaker and getting a funnel, and then just pouring in your sample directly into the burette with the funnel in it. So you use a funnel to make sure that none of your solution spills out on the sides, and you can just load it into the burette directly. So once you've formed your standard solutions, again, should I make a video on standard solutions? Maybe I should, I don't know. Leave it in the comment section if you want me to explain how standard solution works. They're very easy. But once you've done all of that, and you've loaded your burette, you've set up your apparatus, it should look something like this. And I drew this. Hopefully it's an accurate represent. It should be. Yes, this is. I drew this, so bear with me if there's anything that's like kind of out of order or not exactly in place, but I tried. So this is, and I know the handwriting might be not bit easy to see, but this is an acid base reaction. Now this is a strong acid with a weak base. Ammonia is a weak base with dilute sulfuric acid. I know sulfuric acid isn't blue. It's colorless, but I've just done it in blue so it can be easy to see what's being dripped down. The top is a meniscus line, and that's quite important to highlight. And now you're not never gonna tell you to write down a meniscus line, but it's something that you'll see when you're doing your titration, and it's very important that you don't uh, take for granted it because you don't take it for granted because when you're doing a titration reaction, or when you're using a burette in general, it has something called the meniscus. Now it looks like a dip on the top of your top layer, and it's important that you look at the bottom. So if you're ever thinking of how do I measure, if how do I measure this line, like when it stops, right? You measure from here, not from here, not from this part here, right? You don't measure from the bottom. So you don't measure from the top, you measure from the bottom part here. That's the part in science that we use to measure the meniscus line. It's the bottom part, not the sides. Now the reason why this happens scientifically, if you think so, why does that happen? Is because the solution is attracted to the walls of the burette, to the glass container. That's why it's causing it to kind of bend in that way. So the solution is actually attracted to the walls container, and that's what causes that meniscus line. The bottom, the mid part, the part in the middle isn't attracted to anything because it's the furthest away from the walls. But the parts next to the solution that's next to the walls is going to be very much attracted to it, and it causes this little meniscus line. But it's very important you read from the bottom of the meniscus line, and not from the top. Now this is dilute sulfuric acid inside a burette. You have your tap, make sure that's closed, and then you kind of open it when you need to do so. You make sure you have your of course I have my stand here, metal support stand here, and I have a clamp with well, it's just a clamp you can see to help align my burette, and I have a conical flask here that's directly underneath your burette. Now I draw this out because they may ask you in exam to draw a diagram of this type of reaction, of how to set it up, and they may ask you to label it. Now I mean the support stand you maybe have to label, and the clamp you probably have to label. But the most important thing that if they ever do ask you to label any of this is here, and you should have done titrations from from if you've done triple science, you would be aware of what titrations are. So this isn't really too much of a difficulty for you. But for someone that's doing this for the first time, if you've done double science, then I guess really this is something new to you, or not. This is year 2 work anyway. But it's important that you label the dilute sulfuric acid inside the burette, and you have the tap here. Very important that you mention the tap. Some mark schemes don't care about too much, but I think AQA does care about too much. Don't draw the drop. That's not something that they want you to do. Just don't need to draw the drop, but show it as a close. I've shown it open here, but show it as a closed tap. In fact, you can write closed tap. Now it's important you actually mention the ammonia solution with an indicator. Now, if you understand if you understand why we use an indicator, then you'd understand why it's important to mention it. I'll go through indicators, why they're useful, why we talk about them in chemistry, but I'll go through that later. But this is the apparatus that we're using, and this is an ammonia solution, which is a base, and if a methyl orange indicator, because we're adding methyl orange in particular goes from a yellowish color towards red when it's going more basic, when it's going more acidic. As you see, we're adding acid here, so it should be turning eventually more acidic, and we'll see a color change here. If they ever ask what improvements could be done to this type of mechanism, I should have done this part at the end really, but if they ever ask you what improvements you could make to this diagram here, it's very, very, very kind of expensive to do this. But the best thing is, the most important thing you could say to this is, if they ever ask to improve, you could say you can use a colorimeter to help determine when the color change happens, and attach that to your computer. That could tell you exactly when the reaction has actually changed, or the color change has happened. That's a very expensive way, but I think the most important thing is just to say that if they ever ask you in separate questions, to saying that you have the same person looking at the time, looking at when the reaction changes, so there's no difference in reaction time. But that is it. Now, I actually want to close this off because 1 second. Here we go. Now, accuracy. So in a titration, you want to make sure that you have accurate results. Now, accurate results are achieved by repeating your titration until you get concordant results, is what we call them. Now, concordant results are values that are within 0.1 centimeters cubed. Now, this is very, very important, because when you're doing your titrations, you'll get your titer values. If your titer values aren't within, you'll do a scratch value, and then you know, a rough approximate value to see where roughly your reaction happens. You have an idea of roughly when doing your calculations anyway, but you'll do that, and you'll do 3 separate titers. So you'll repeat the experiment 3 times, so that you can just make sure you get an accurate representation. Now, if you get titer values that are outside your 0.1 centimeter cubed range, you discount them. They're counted as anomalous results. You only count results that are within 0.1 centimeters cubed. That's what we call concordant results. Now, this kind of brought me on to this. I saw this part here, accuracy, and I thought about this is a very, very important thing that they may ask it. They don't usually ask it in chemistry, ask it more in biology, but in case they do ask it, and sometimes people get confused between it, the difference between accuracy and precision. Now, accuracy is a measurement of results sorry, a measurement a measurement result is considered accurate if it's judged to be close to the true value. So an accurate result is results that are close to a true value. When we're talking about accuracy, is how close the values are to the true value, right? Precision, now precise measurements are ones in which there is very little spread about the mean value. Precision depends on the extent of random errors. It gives no indication of how close results are to the true value. Now, so these are all the definitions from AQA. So if you ever ask for this here, but essentially what this is, that accuracy is how far your results are from the true value, and precision is how close your results are. In terms, if you were to like draw a mean, they'd be roughly close to one another, right? Now, if that's hard for you to guys to understand, I'll draw it out like this. So let's say I had this little archery board, right? That's a terrible thing there. Now let's use that, right? So let's say there's a little archery board here. This isn't the best example here. I mean, actually, yes, yeah, I think this is good as well. So say that we wanted to hit this little spot here, right? This little center point here, all right? That's the area that we're trying to hit. An accurate result would be this, right? If I hit there, that's considered to be an accurate result, right? Whereas these are not accurate results. These 3 results here are not accurate results, because then they're further away from this value here. But these results are more precise shots because they're more close to one another. These shots are the most closer, they're more precise to this point here. If we add the point here, they're the most close to one another. They're not dependent on them actually being close to the true value, but there's consistent precision here in terms of the fact that they're the most close to one another. Now, if they ever ask you, if they're never gonna ask you an example, right? But let's say they were asking for you to. I think the best way I can say, let's say you're taking a penalty, right? I'm gonna bring this a random example, a football example, right? And they're telling you to hit the top right hand corner, right? They're telling you to hit the top right hand corner of the goal, to kick the ball into the top right hand corner of the goal. That's accuracy. but you keep skying the ball over. Now there's a couple people probably muffling, like looking at their friends probably weirdly, but if you consistently hit a certain part of like the sky every time you kick the ball over, that's precise. Or if you keep kicking it just above the post, that's precise. It's not accurate because it's not necessarily anywhere near your the true value. You could be on the going towards the left. It could be going wayward, you know. But if you keep consistently hitting the same area, that's precise. It may not be accurate. Now, you can have precision with accuracy, but it's you don't have accuracy with precision, if that makes any sense. Your results can be so these here, if these were here, right? That's precision and it's still quite accurate. But what we have up here, oh, these are very precise because they're very close to one another. They're weirdly precise. And if we're doing a mean here, we say the mean. If we were to draw a mean, we say that the area that we would aim for really is here, right? That's the mean, or that's the most precise value that we had. They're very precise to being in that area, but accuracy wise, very poor because they're very far away from the actual area that they're trying to hit. Now, I probably emphasize that probably way too much, but I just wanted to make that very clear, and that's it. So, I'll move on from that. Now, indicators. So to find an endpoint of a titration, you use an indicator. Now, an indicator, as I brought up here, why we use an indicator, right? An indicator changes color when all unknown reactions is used up. Now, I've got an example of a strong acid / base titration, right? So we use there's a number of different indicators that we'd use, and I'll give a couple of examples later. But all it does is that once the reaction's gone to completion, the indicator rapidly changes color, telling us that the reaction is under completion. So if we're going from very basic and we're adding base to our let's use this example here, right? We're adding acid to this base. Now we're trying to neutralize this base with acid. Now, if we were to work out the pH of this solution here right now, if we were to work out the pH of this solution right now, we have the pH probe in here of some sorts, right? I know it's not a good pH probe, but I'm just trying to. Oh, it's terrible, right? But we say that is a very, very high pH because it's a base. Well, no, so not very, very high pH. It's a weak base, so roughly 10, I'd say, maybe 10, 9, 9-ish pH. But it's basic, right? A pH of roughly 9. Over time, we add acid and that neutralizes the base. So it's only slightly becoming less basic. So only it decreases slightly, very, very slightly. It'll look a bit like this, right? And then it go a little bit down, not drastically. Once all the base has been neutralized, it goes down like this. I'll show you an example of a similar type of reaction. It's actually going in the opposite direction, but it drastically drops and then it comes to go to acid. That's the one thing of these types of acid-base reactions. They're very, very instant changes. Very, very instant changes. They're so instant and they're so difficult to see that if we didn't have an indicator, remember these are colorless solutions most of the time, right? You wouldn't be able to tell when the reaction's gone to completion because they're colorless. Because they're one of course they're colorless, and the reaction is so instant. So we use an indicator to just help us understand when the reaction's actually gone to completion. And that's it. I'll just go back to here. So strong acid-base titration. So titrations of a strong acid with a strong base are the simplest to understand. So I've got an example of a strong acid-base titration, and it's the most easiest one to understand, right? So pH curve. So I've got a pH curve pictured below, and that shows the change in pH when a strong acid is titrated with a strong base. The direction of the curve is dependent on what you put. So I want to make this clear, right? The direction, as I said before here, that the example that I shown here is this is a base acid reaction. We're adding an acid to a base, right? But the direction of this curve, this is going in a downwards motion. The direction of this curve is dependent on what you put in your beaker and what you put in your burette. This isn't really something that's crazy to understand. It's very basic to understand. If we're going upwards, if we're going from a very low pH to a very high pH, it means that we've put, instead of having, you can think, you probably work out yourself. If this has a very very low pH and this is a very, and I say this, I remember you guys can't see what I'm showing you. If our if our conical flask has a very very low pH and our burette has a very very high pH, it just means that we swapped it round. And you can use it either way around, just depends on what you want to do. In this example here, I've chosen to titrate the base with the acid, but you could titrate the acid with the base. And if you did that, it would be the exact same concept, but it would just be flipped. Oh, and this is what you're going to see. This curve is now, this is for an acid base reaction. The length of that equivalence point can differ depending on how strong your acids or bases are. But I just wanted to give you, that's all I was just trying to say, this little part here, right? That the direction of the curve is dependent on what you put in your beaker and what you put in your burette. The example below is of a strong acid measured in the beaker being titrated against with a strong base. That's used to dilute the acid as it's being released from the burette into the beaker, and this causes the trend in the graph below. However, if you flip things around, the same equipment but had the acid in the burette and the base in the beaker, you just flip your graph horizontally from the equivalence point. What is the equivalence point? You'll see below. Now, as I said before, this is the reaction of uh, uh, an acid being titrated, an acid which is in our conical flask being titrated against with a base that's going to be in our burette. So what we see here is that, and I go through this, right? We have, this is, let's just say that this is the, yeah, I'll separate into this. So say that this is our beginning, middle, and then end, right? In the beginning, you can see that the pH is very low and doesn't change very quickly. Now, there's this little part here is a perfect example of something that we call a buffer in chemistry. And if you guys know what a buffer is, right, acids do this very well. This is why there's such a dramatic change in pH. Base acids or bases do this very well. They act as buffers. Now think about it carefully, right? What do buffers do? Buffers just if you go back to chemistry or even biology, right? What does a buffer do? A buffer just maintains the pH. If you're talking about an acidic buffer, any type of buffer just maintains. Buffers just in general maintain, but if we're talking about an acid or base buffer, they just maintain the pH. If we're talking about an acid buffer, right? An acid buffer is very good at maintaining a very low pH, consistently keeping a very low pH. And what you have here is that you're adding, as we're adding, now imagine this was flipped, right? Imagine this was flipped. This was the base and this was the acid, right? I mean the same principle applies here, right? But it's just a different way around it. You know, we're adding this. Actually, you know what? I'll just say how it is so that I don't confuse you too much. Let's just keep it as it is. This is the sulfuric acid, and this is ammonia base in our conical flask, right? As we're adding acid, the pH doesn't change quickly because there's more base than acid to counter, so the overall pH doesn't change, right? So you can keep adding it, we keep adding it, we keep adding it, right? So we have more. Let's just say it like this, right? I know it's not like this in our we have, it's not OH minus, but you get the general theme, right? We can add, if we had more, I won't use OH minus, I'll use A minus. A minus, A minus, A minus, A minus. If there's only 2 H pluses being added here, these would get neutralized. There's still more A minuses, there's still more base than there is acid. So the pH still wouldn't change very much. And it's the same principle here. If there was more acid in our solution than base, then the graph wouldn't change that much here in this little part here. That's what's happening in the beginning. Now, there comes a point in the graph, right, where there comes a point in the reaction, and it's a very, very instantaneous point, right, where we have now, if I got rid of these two rings here, right, let's say I get to this point here, right, where let's just add a couple more A minuses. So we add now, we get to a point in a reaction where there's now just four, it's 5, 6. 2, 4, 6. Great, right? There comes a point in the reaction where we have, it's now being great. We've now have as many bays as, now this is a very, very precise period in the reaction. We have the same number of bays as we do acid. It's neutral now at this point here, and at this point here that there's no overall change until, now if we're using this example here where we're adding acid, we just have one more H plus than A minus. Now the graph would change dramatically, right? It'll be going, this is, and I'm gonna use this example here because this is the one that we have. I'm using this example here because that's technically what the reaction is. Once we have the same number of H plus as A minus, we reach this point here. Now it's this is where we start to the graph starts to peak. As soon as it has more H plus than A minus. So yeah, if we're using this, as soon as it has more H plus than A minus, it dramatically goes straight down. Like if you look at many of these H plus, these are pH curve graphs, right? It's not a gradual curve. It's a spike. It's a spike, and drops down to here. This point here in the middle is called the equivalence point. Now, go back to this here, right? In the middle of the graph, there's a sharp change and the pH rises. If we're using it back to this graph here, right? It's the same principle, just that we're having different type of solutions in our beaker, right? This is using a base. The one that I've used is a acid in our beaker, and we're making it more basic. But the same principle here, if we're having more, the minute we have more A minus in this, the minute we have more A minus than H plus, so here, so that the part I've circled is when you have the same number of H plus and A minus. As soon as you go over that, you spike right up to here. Now, at this, so in the middle of the graph, there's a sharp change and the pH rises very rapidly, and this is known as the equivalence point. At the equivalence point, the acid just about neutralized. So this is, I say this graph probably isn't the best. I try to draw it myself. It's a point, right? And this is actually more like, it's closer to like, the graph actually goes, it's a bit more steeper. It's a bit more like here, really, right? But it's clear to see that this equivalence point here, sorry, that's really where the H plus and the A minus is equal. That's the, it's just that it's so quick, you don't really have time to kind of see it, and you're more likely to think about it as being down here. In reality, this middle part here where the graph kind of goes up and down, that's the real equivalence point where H plus is equal to the base. The concentration of H plus is equal to the concentration of our base in our solution. That's what the equivalence point represents. Now the curve ends at a very high pH because the solution has an excess base than present. So if I'm using for this example here, right, there's more, we've now reached a point where there's way more, I say way more, but there's more A minus than H plus. Not this point, to be honest, the equivalence point is almost like, if we're using this example here, A minus is more than or equal to H plus, because as soon as it goes to it's so hard to instantly. That's if you look at your actual reaction, it's such an instant change, so you wouldn't really be looking at it. It kind of reminds me of the iodine clock test, right? Right, the color change is so quick. Okay, maybe the iodine clock test is a bit more faster, but in principle, right, once it's gone past that equivalence point, I like to think of it more as more than or equal to is the equivalence point, because it's really, actually that's probably not a good example. I don't want to confuse you guys anymore. So I'm not going to confuse you. I'm not going to confuse you. Just use this. Just use this. I'm not going to confuse you anymore. Use this. H plus is equal to A minus. I'm not going to confuse you anymore. H plus is equal to A minus is the equivalence point. But as soon as it gets past that equivalence point, A minus is greater than your H plus. And it just stays like that. Here, you've now kind of just got a constant solution of base. Any acid that may be left over, it's more like a buffer again, where there's more A minus than H plus, so it can consistently keep acting as a almost like a basic buffer in that point, right? All right, so indicators. So when doing an acid-base titration, you need to use an indicator to find the equivalence point, and a good indicator will change color dramatically over a small pH range. If the small pH range includes the range of the equivalence point, it's a great indicator for the reaction. So all this is saying is that a good indicator changes pH over a small, so it changes color over a small pH, and if your indicator changes color in that pH change, so if the pH if the pH that changes is between, in this case, what, say what, 1 and roughly 1 and up to nearly 14 in this example, it'll be a good indicator. Now any indicator in this reaction, most indicators are between 1 and 14 anyway, so you'll be fine on that aspect. But you may get examples when in the part 3 video I'll show you examples where probably I haven't decided if I'm going to do this in the part 2 or the part 3, but you'll have your color change, whereas if you're using a weak acid, right, if your weak acid is starting here, you see, having a indicator that changes color from this type of pH range, right, between 1 and 5, would be useless because our color change isn't happening there. So that's all I'm trying to say here, that you want to use one if a good pH change, a good indicator here. We were looking for an indicator that changes color between roughly anywhere between really, what, 7, maybe 8 to 12. You can say 7 to, well, 8 to 12. 8 to 12 is a good indicator, right? And there's two main ones that you should know, but there are plenty of examples. But there's the two main ones that you need to know. So the two main indicators of phenolphthalein and methyl orange. Phenolphthalein changes from colorless to pink, when it's anywhere from 8.3 to 10. So when it's going in the basic direction, it changes color from colorless to pink. Whereas if you're going in the basic to acidic direction, it changes color from pink to colorless. If that makes any sense, hopefully that would make perfect sense there. But in this example here, in this particular example, because we're going in a more basic route, our indicator will go from colorless to pink when the reaction has basically reached the equivalence point, right? We could also use, in this case, methyl orange, which is the one I've used at the top, right? For the reaction I've used above. It changes color from anywhere from red to yellow between the pH of 3.1 to 4.4. So the reason why I've used the one above, so methyl orange changes color from red. So when it's going from in a more basic direction from 3 to 4.4, it goes from red to yellow, and if it's going in in an acidic direction, changes color from yellow to red within the range of 3.1 to 4.4. Now the first example that I shown, I used methyl orange because we're using a very, very strong acid, which is H2SO4, right? You're using a very, very strong acid in H2SO4, and a very, very weak base in ammonia. So I can tell originally right now that our equivalence point is going to be like roughly here, right? Because think about it, right? We're doing this, sorry, low pH is probably like a 9, and then, sorry. So I want something that's going to change cut. Again, that's a terrible. I want something that's going to change pH roughly here. The equivalence point is roughly there, right? So we need anything within that sort of range between 3.3 to 4.4. So, and that would be a perfect indicator to do that there. So, yeah, that's why I used that for that example there. It will be going from, in this case, it'll be going from yellow to red. There'll be a sharp color change there. So either of these are well suited for the strong acid-base titration I've used above this with this one here, but in other examples you need to use more specific types of indicators. Now, calculations for titrations, right? So you've probably seen this type of case. I'm gonna go through this part quite quickly because you should know how to do these types of reactions. So we've seen before how to carry out titration calculations using titer. I shouldn't say tire. It's titer. Will it convert? Here we go. Titer values and balance equations. So we're going to quickly recap on some of these calculations, right? So information. I don't know why I don't know why my thing isn't. I'm not gonna. You know that's information provided, right? Before starting your calculation, you'll be given your balanced equation for the ratio. Sometimes you're not going to be given your balanced equation. Sometimes you need to calculate to generate your own balanced equation. So you should know how to balance an equation. The volume and concentration of the titer and the volume of the other reactant. Now you may not be given that. Maybe they give you the moles of the compound or whatever. But most likely you need to work out. I mean, you're most likely gonna have to work out the moles from your known concentration of your solution, right? You'll know the volume, you'll know the concentration. You may not know the volume, it may give you the concentration the most. I don't know the exact sample in your exam, but the point being is that you should know how to rearrange your equation to work out whatever you need. That's the most important part. They'll take away one thing, and you just need to be able to use that information to work out the information that you already have to work out another. They may give you only one information, but they may give you enough information to work out to work out the other value to then use it into your equation, right? So all these things will give you enough information to ultimately come back to the formula concentration is equal to moles over volume and then rearrange. You'll most often be asked to find the concentration of this other reactant. Now, the first step is calculating the moles of the titer using the two pieces of information that we know about the titer, so the volume and the concentration. We use the equation moles is equal to volume times by concentration. Now, the second step is that we find the number of moles of the other component. A titration is stopped. So this is when we do our titration. The titration is stopped at the exact point of neutralization. So we can assume that the mole ratio will be the same as in the balanced equation. Because remember, a titration is stopped at the exact point of neutralization. So it's fair to make the assumption that saying that the mole ratio is the exact same as in the balanced equation. For example, if the mole ratio from the equation was 1 to 1, the component will have the same number of moles as the titer, exact same, because we're just doing the reaction to completion, so it'll follow the exact same principle. If the mole ratio was from the equation was 2 to 1, the component will have twice as many moles as the titer, which is what we'd expect. Right, so you don't need to think about it any differently. It's literally treating this the exact same as a concentration, moles and volume calculation question, because titrations follow that same principle. The reactions go until completion, until all of the reactants are used up, or until all of the acid is used up, or all of the base is used up. So, and when I mean all of the base is used up, all of the moles of base are used up, or all of the moles of acid are used up, right? So that's why you can make these assumptions. Now, the first step is finding the concentration of the other component. we can rearrange the equation moles equal to concentration times by volume into concentration is equal to moles over volume. And the units for this are very important in titration calculations, where moles is equal to mol, we represent it as mol. Volume is decimeters cubed and not meters, not centimeters cubed. They always, I mean, this, as you do, as I said, if you want to become good at exam questions, you need to know how to. So if you want to know, if you want to be good at chemistry, or just understand chemistry very well, the best thing to do is to actually to answer exam questions, because you can know the content very well, but it means absolutely fuck all if you don't really know how to answer exam type questions. They don't care about if you know the content very well. No one cares if you know the content very well. The only thing that matters is you may know someone doesn't know the content as well as you do, but they know how to answer exam questions better than you, and that's what matters at the end of the day, right? So the best way to know the topic is to be say I can answer the questions. That's the best way of knowing the content. And for certain, from what I've seen, is that forgetting to convert the volume from centimeters cubed to decimeters cubed is where most people make the mistake. But if you do constant exam questions, you just don't make that mistake. I never make that mistake. Whenever I see the volume, I always know to convert it to decimeters cubed. So I always times it by 10 to the power of minus 3, or that's timesing it by 0.001 decimeters cubed, or dividing, if that's too complicated for you, timesing it by 10 to the power of minus 3 or timesing it by 0.001 is the exact same as dividing by 1,000, right? That's all it is. That's all you, so to go from centimeters cubed to decimeters cubed, dividing it by 1,000, right? I remember that if you're doing moles over decimeters cubed, which is what moles over volume, if you're doing mole over decimeters cubed, that's moles over volume, so that's moles per dm cubed. All right, that's it for this video. Hopefully this